64 million miles from Earth, a space rock smaller than a football stadium turned out to be hiding something nobody on the NASA team expected. A second, smaller rock, quietly circling it like a shadow that refused to leave. Nobody on the mission team saw this coming, not in any of the years of planning. Stick around, because this is only the first surprise in a story that gets stranger the further a tiny spacecraft named Lucy travels from home. And before we get into how strange this really gets, subscribe now if you want to know the moment Lucy finds something new out near Jupiter. Because this spacecraft is just getting started and the biggest discoveries are still ahead of it. This is the story of NASA's Lucy mission, a spacecraft the size of a small car that is flying further than almost anything humans have ever built, chasing after ancient rocks that have been drifting near Jupiter since before the Earth had continents. Along the way, Lucy has already stopped scientists in their tracks twice. And very recently, in the summer of 2026, a brand new study came out that made researchers rethink what they thought they knew about one of the asteroids Lucy flew past. This is a story about being wrong and then being amazed by exactly how wrong you were. Let us start from the beginning, because most people believe space missions like this one are simple. You build a spacecraft, you point it at a target, you take a picture, and you're done. That is not even close to what happened here. Lucy was not built to visit one asteroid. It was built to visit 8 of them over 12 years, using a flight path so complicated that it loops back past Earth not once, but twice, just to steal enough speed from our planet's gravity to make it all the way out to Jupiter. Nothing about this mission is simple, and that is exactly why it has already surprised everyone involved. Lucy launched on October 16, 2021, from Cape Canaveral in Florida, riding on top of an Atlas V rocket built by United Launch Alliance. The spacecraft itself was built by Lockheed Martin, and it is genuinely huge, stretching about 43 feet long once its 2 giant solar panels unfold, roughly the length of a school bus. Those panels are not just big for show. Out near Jupiter, sunlight is so weak that Lucy only receives about 500 watts of power at its faintest, dimmest encounter. 500 watts is barely enough to run 2 hairdryers, and Lucy has to run every camera, every heater, and every radio system on that. Here is the part almost nobody expects. Lucy is not named after a place or a scientist in the usual sense. It is named after a 3.2 million-year-old human ancestor, a partial skeleton discovered in Ethiopia in 1974 by a paleoanthropologist named Donald Johansson. That skeleton, nicknamed Lucy, helped rewrite the story of human origins. NASA borrowed the name on purpose because the asteroids this spacecraft is chasing are considered fossils too, just fossils of the entire solar system instead of fossils of one species. Lucy also carries 3 main scientific instruments packed onto its frame. There is a high-resolution camera called LaLaurie, built to take sharp black and white pictures from far away. There's an instrument called LaRalph, which studies color and chemical fingerprints using both visible and near-infrared light. And there is a heat-sensing instrument called LITES, which measures temperature differences across an asteroid's surface, almost like a thermometer that can read heat from hundreds of miles away without ever touching what it is measuring. The asteroids Lucy is heading toward are called Trojans, and they orbit the Sun in 2 loose swarms, one running ahead of Jupiter and one trailing behind it, both trapped there by Jupiter's enormous gravity like leaves caught in a slow-moving eddy of a river. Scientists believe these Trojan asteroids have been sitting in roughly the same spot since the solar system first formed, about 4.5 billion years ago. That means studying them is a little like digging up a time capsule that nobody has opened since before Earth had oceans, before Earth had a moon in its current position, before Earth had anything alive on it at all. But here is where the underdog part of the story begins, because for a long time, Trojan asteroids were treated as an afterthought. Big, glamorous missions went to Mars, to the Moon, to Saturn's rings. Small, dark, distant rocks trapped near Jupiter's orbit did not get the same attention, mostly because they are hard to see and even harder to reach. It took NASA's Discovery program picking Lucy as mission number 13, back on January 4th, 2017, before anyone committed serious money and serious years to actually going there. The rocks nobody wanted to visit turned out to be some of the most important rocks in the entire solar system. Think about it like a school science fair where the judges walk straight past the strange, dusty, unglamorous project in the back corner, because it does not look flashy on the surface. Then, months later, that same overlooked project turns out to hold the answer everyone else was searching for. That is essentially what happened with Trojan asteroids. They sat quietly, unglamorous and dark, until one mission finally decided they were worth an entire decade of careful attention. While Lucy makes its long 6-year journey out toward Jupiter, the mission team decided not to waste the trip. On the way, Lucy would pass close to 2 smaller asteroids sitting in the main asteroid belt between Mars and Jupiter, not as the main goal, but as a warm-up, a dress rehearsal for the real encounter still years away. Nobody expected those warm-up flybys to produce anything historic. That assumption did not survive contact with reality. The first warm-up target was a small asteroid called Dinkanesh, only about 738 meters wide, roughly 7 football fields end to end. On November 1st, 2023, Lucy sped past it at high speed, snapping pictures the whole time. Scientists expected a simple, single, boring space rock, something to test the cameras on before the real mission began. What Lucy actually found was a rock that was not alone. Hidden right next to Dinkanesh, almost too small to notice at first glance, was a second object, a tiny satellite now named Selim, orbiting its larger companion like a moon orbits a planet, except this moon looked strange. Instead of being one solid ball, Selim turned out to be what scientists call a contact binary, which is a fancy way of saying it is actually 2 smaller rocks that gently bumped into each other a long time ago and have been stuck together ever since, like 2 marbles glued end to end. Nobody on the science team was expecting a double object hiding inside what looked like a single tiny moon. That discovery compresses down to something almost anyone can picture. Imagine finding out that a pebble you noticed, rolling next to a bigger rock in your driveway, was actually 2 pebbles fused together the whole time, and you only found out because you happened to look at it from exactly the right angle at exactly the right moment. That is essentially what happened, except this pebble is millions of miles from Earth, and the right angle required a spacecraft traveling at roughly 10,000 miles an hour. Researchers led by scientist E. B. Bierhaus and a team of colleagues published a detailed study of Dinkanesh and Selim in the Planetary Science Journal in 2025, laying out exactly how the 2 lumps of Selim likely formed and slowly drifted together under weak gravity. Weak is an understatement. Selim is so small that its gravity is barely strong enough to hold a person down if you were somehow standing on it, nowhere near strong enough to crush 2 objects together the way gravity works here on Earth. And yet, over a very long time, it happened anyway. There is something almost eerie about picturing that moment happening in complete silence. 2 small rocks, drifting for who knows how many millions of years, slowly, gently touching for the first time, at a speed probably slower than a person walking across a kitchen floor. No explosion, no dramatic collision, just a quiet, patient meeting between 2 pieces of leftover material that eventually settled into becoming one single object, floating together ever since. Are you starting to see why this little spacecraft has already earned so much attention, even before it reaches its real targets? If so, leave a comment telling me which part of this story surprised you the most so far, because it genuinely helps me figure out which details you want me to dig deeper into on this channel. Let us jump back to scale for a second, because it is easy to lose track of just how far away all of this is happening. Dinkanesh sits roughly 300 million miles from Earth at its closest, which is more than 3 times the distance between the Earth and the Sun. Meanwhile, back on Lucy itself, the spacecraft's onboard computer runs on less processing power than a basic kitchen microwave, because deep space missions rely on older, heavily tested chips that are far less likely to fail after years of radiation exposure. Enormous distance, tiny amounts of computing power, and somehow still historic discoveries. It is worth pausing on that microwave comparison for a second, because it tells you something important about how deep space missions are actually built. Engineers do not choose the newest, fastest computer chips available for a mission like this. They choose older, slower, heavily tested chips instead, because those chips have a long track record of surviving years of radiation exposure without glitching. In deep space, boring and reliable almost always beats fast and flashy, since there is nobody available to fly out and fix a broken circuit board hundreds of millions of miles from home. After the surprise at Dinkanesh, the Lucy team had one more warm-up flyby scheduled before the real Trojan encounters could begin. This next target was an asteroid called Donald Johansson, named directly after the same paleoanthropologist who discovered the Lucy fossil back in 1974. On April 20th, 2025, Lucy flew past this asteroid at a distance of about 596 miles, closer than the distance from New York City to Chicago, moving at roughly 30,000 miles an hour as it went. Scientists expected Donald Johansson to be a fairly typical, somewhat elongated rock, based on earlier telescope observations from Earth. What Lucy's cameras actually revealed was something far stranger. A bilobed asteroid, meaning it looks like 2 separate lumps pressed together at a narrow, pinched middle, almost like a lopsided dumbbell or 2 scoops of ice cream that have partly melted into one blob. It was not smooth, it was not simple, it was a battered, complicated shape that immediately raised new questions about how it had formed. The second surprise came from watching how Donald Johansson moves through space. Most asteroids simply spin steadily on one axis, the way a top spins on a table. Donald Johansson instead tumbles, rotating in a wobbling, unstable way that scientists compare to a slowly toppling top that never quite falls over. That kind of tumbling motion tells researchers that something violent happened to this asteroid a long time ago, most likely a massive collision that knocked it off any calm, steady spin and left it wobbling ever since. A detailed study of these findings, titled "The Lucy Flyby of Donald Johansson, a bilobed asteroid with tumbling rotation," was published in the journal Science in 2026, describing the asteroid's shape, its strange spin, and what both of those details suggest about its violent past. The study estimates that Donald Johansson formed from a collision roughly 150 million years ago, meaning this lumpy, tumbling rock has been quietly wobbling through space since before many dinosaur species even existed on Earth. Here is the three-beat surprise laid out plainly, the way scientists themselves experienced it. First, they expected a simple, single, elongated rock based on distant telescope images. Second, they found a bilobed, tumbling, collision-scarred object with a complicated two-lobed shape. Third, and this is the part that makes it click, picture two snowballs mashed together by a kid who was not paying attention. Then, imagine that clumsy snowball surviving, spinning, and tumbling silently through space for 150 million years without anyone noticing until now. Has this made you think differently about what a simple flyby mission can actually accomplish? If this story is hitting the way I hope it is, hit that like button and tell me why in the comments, because it genuinely tells the YouTube system that stories about missions like Lucy deserve to reach more people who would enjoy them. Let us zoom back out to the domestic scale for a moment, because these huge numbers can start to blur together if we do not anchor them to something familiar. Donald Johansson is roughly 5 miles long at its longest point, about the length of 88 football fields laid end to end, or roughly the distance you would drive across a medium-sized town. To put its size another way, Donald Johansson is only about half the width of a typical American county. Yet from Lucy's camera, it appeared as nothing more than a tiny, irregular smudge until the spacecraft got close enough for real detail to emerge. And the data Lucy collected during that single 600-mile-per-hour fast flyby took engineers on Earth several months to fully process, roughly the same amount of time it takes a single school year to unfold from September to June. Now for the underdog twist inside this particular part of the story. Before Lucy's flyby, Donald Johansson was considered one of the least interesting stops on the entire journey. A quick technical test with low expectations attached to it. Researchers were treating it almost like a formality, a box to check before the mission moved on to its real, headline-grabbing Trojan targets. Instead, this boring warm-up asteroid ended up producing one of the clearest examples scientists have ever captured of a violent, ancient collision frozen in stone, tumbling silently through space for our cameras to finally catch. There's a particular kind of humility built into that discovery. The team was not hunting for a dramatic collision story when they pointed Lucy toward Donald Johansson. They were simply testing equipment, checking boxes, making sure the cameras and pointing systems worked correctly before the mission's true targets arrived. Sometimes the most meaningful discoveries in science do not come from the experiment you were planning. They come from quietly paying close attention during the parts of the plan everyone assumed would be routine. This is where scientists themselves admit they still do not fully understand everything they are looking at. Researchers studying Donald Johansson will tell you plainly that the exact sequence of the ancient collision, how fast the impacting object was moving, what angle it struck at, and how the two lobes settled into their current shape afterward, is still debated within the planetary science community. The models built before the flyby predicted a somewhat different shape than what Lucy's cameras actually captured, and reconciling that gap is still ongoing work at institutions like NASA Goddard Space Flight Center and the Southwest Research Institute, sometimes shortened to SWRI, which leads the Lucy science team. That gap between prediction and reality is not a failure. In many ways, it is the entire point of sending a spacecraft instead of relying only on telescopes and computer models from Earth. A telescope sitting on our planet, even a powerful one, can only guess at shapes and spins from far away. Only a spacecraft flying close enough to feel the asteroid's faint gravity, close enough to see individual boulders and craters, can actually catch the universe being more complicated than anyone predicted on paper. And that brings us to why the summer of 2026 mattered so much for this mission. The Science Journal study confirming Donald Johansson's bilobed tumbling nature was formally published on June 18, 2026, more than a year after the actual flyby took place, because it takes that long for scientists to carefully cross-check images, measurements, and computer models before publishing conclusions the entire scientific community can trust. That single sentence in a research paper describing a tumbling, two-lobed asteroid represents more than a year of careful, unglamorous, behind-the-scenes work by dozens of researchers. That kind of patience runs through almost every part of this mission. Engineers at NASA Goddard and scientists at institutions across the country spent that entire year double-checking measurements, comparing computer models against real photographs, and rerunning calculations to make sure nothing had been misread. A single sentence describing a tumbling bilobed asteroid sounds simple when you hear it in a video like this one. but it sits on top of an enormous, quiet mountain of careful, patient verification work that most viewers will never see. Meanwhile, as all of this analysis was happening back on Earth, Lucy itself never stopped moving. The spacecraft kept coasting further and further from home, conserving fuel, running quiet system checks, slowly closing the distance toward its real, primary destination. Right now, in the spring and summer of 2026, mission engineers have begun turning Lucy's cameras toward its upcoming Trojan targets for the very first time, even though the spacecraft is still hundreds of millions of miles away from actually reaching them. Up until this point, almost every image of these Trojan asteroids has come from telescopes sitting right here on Earth, all looking from roughly the same angle as the Sun, which makes each asteroid appear fully lit, almost like a small, bright coin. Lucy's early test images are the first time in history anyone has looked at these particular objects from a different direction, and that shift in angle matters more than it might sound. From a new angle, part of each asteroid falls into shadow, revealing bumps, ridges, and craters that a fully lit, coin-like view could never show. Would you want to see exactly what those first distant test images looked like? Let me know by sharing this video with someone who would find this as fascinating as you clearly do, because a mission this quiet deserves a much bigger audience than it currently has. Those early test images are almost unbelievably unglamorous to look at. From this current distance, the Trojan asteroids Lucy is chasing appear as nothing more than tiny, faint pinpricks of light, barely distinguishable from background stars. Between March and April of 2026, Lucy pointed its high-resolution camera called Lilori toward 4 separate targets: Euripides, Polymele, Lucas, and Oris. Engineers spent until July of 2026 downlinking and carefully processing those faint images, all just to fine-tune camera settings months and years before the real encounters even happen. Why bother testing this early, this carefully, for objects that still look like single pixels of light? Because when Lucy finally does reach these asteroids, it will be moving unbelievably fast, up to 16,000 miles an hour relative to its targets, and it will only get one single close pass at each one. There is no pausing, no circling back, no second attempt, if the camera settings are wrong. Every setting has to be nearly perfect on the very first try, which is why the team is testing cameras on tiny, distant specks of light years ahead of time. Imagine trying to photograph a single moving firefly from across a football field at night. Using a camera, you're only allowed to fire once, with no chance to check the picture and try again. That is roughly the level of precision the Lucy team is preparing for, except the firefly is millions of miles away, moving at thousands of miles an hour, and the camera itself is riding on a spacecraft that is also moving at nearly the same blistering speed. Here is a comparison that should make that speed feel real. 16,000 miles an hour is roughly 20 times faster than a commercial jet cruising at normal altitude. At that speed, Lucy could cross the entire continental United States in about 11 minutes. And it will be moving that fast while trying to photograph an object that, up close, might only be a few miles wide, coming as close as 300 to 600 miles at its nearest approach to each Trojan asteroid. For comparison, 300 miles is roughly the driving distance between 2 mid-sized cities a few states apart, and Lucy will cover that same distance in about 1 minute during closest approach. Everything about these flybys happens fast, which is exactly why the years of camera testing beforehand matter so much. There will be no slow, careful re-aim once the real encounter begins. The spacecraft gets one narrow window, and every system has to work correctly the very first time. Lucy's first real Trojan encounter is scheduled for August 27, 2027, when it will fly past an asteroid called Euripides and its small companion moon, nicknamed Keta. From there, the mission continues with a flyby of Polymele on September 15, 2027, then Lucas on April 18, 2028, and Oris on November 11, 2028. 4 separate ancient ice and rock time capsules, each one likely holding a slightly different piece of the story of how our solar system originally came together. After that string of flybys, Lucy's path curves back toward Earth for a second gravity assist, borrowing speed from our home planet one more time, before heading back out toward Jupiter's distance for its true grand finale. On March 2, 2033, more than 11 years after launch, Lucy is scheduled to fly past a pair of asteroids called Patroclus and Menelaus, 2 nearly identical objects locked in orbit around each other, considered one of the most valuable remaining targets in the entire mission. Let that timeline sink in for a moment. A spacecraft launched in 2021 will not finish its primary job until Twinava 33, meaning some of the scientists who designed this mission in their 30s and 40s will be watching its final results arrive well into their 50s and 60s. Space exploration on this scale is not built for instant gratification. It is built by people willing to plan a project that outlasts an entire decade of their working lives. Chasing a payoff, most of them will not see clearly until years after they first pressed the button that sent Lucy into the sky. What do you think scientists will find waiting at Euripides in 2027, based on everything Lucy has already surprised us with at Dinkanesh and Donald Johansson? Drop your guess in the comments, because reading your predictions genuinely helps me shape what details to focus on when that flyby footage actually arrives on this channel. It helps to remember why any of this matters beyond simple curiosity. Trojan asteroids are believed to be leftover building blocks from the earliest days of the solar system, material that never fully assembled into a planet, frozen in place by Jupiter's gravity before it could clump together any further. Studying their color, their composition, and their internal structure gives scientists direct clues about which raw ingredients were floating around when Earth itself was still forming, roughly 4.5 billion years ago. There's also a strange sensory quality to imagining what these places are actually like. Out at Jupiter's distance, sunlight is roughly 25 times weaker than it is here on Earth, meaning the Trojan asteroids exist in a permanent deep twilight, a dim gray haze instead of the bright blue sky most of us take for granted every single day. If you somehow stood on one of these rocks, the sun would look like a small, faint, cold light in a mostly black sky, and the silence around you would be absolute, since there is no atmosphere out there to carry any sound at all. The temperature out there would be brutal too, likely dropping to nearly negative 150 degrees Fahrenheit on the surface, cold enough to freeze almost anything you brought with you within minutes. And yet, even in that dark, frozen, silent stillness, these rocks are not empty. They carry frozen chemical fingerprints from the earliest days of the solar system, chemical clues that a warmer, more active place like Earth lost or transformed billions of years ago. That silence is part of what makes this mission feel almost poetic. Lucy is flying toward objects that have been sitting quietly in the dark for 4.5 billion years, untouched, unheated, essentially unchanged since the solar system's earliest chaotic days. Every single flyby, even the test-run flybys at Dinkanesh and Donald Johansson, is really a conversation between a small, humming spacecraft built by human hands and a silent ancient rock that has been waiting in the dark since long before humans, or even dinosaurs, existed on this planet. And that is really the heart of why the Dinkanesh and Donald Johansson surprises matter so much, even though they were only supposed to be warm-up tests. If two unimportant practice flybys could reveal a hidden double moon and a violently tumbling, two-lobed asteroid frozen mid-collision, it raises a genuinely thrilling question about what is waiting at the 5 Trojan asteroids still ahead, objects scientists have never seen up close in the history of human spaceflight. Scientists involved with the mission are careful not to overpromise here. Researchers connected with NASA Goddard and SWRI will openly say they do not know exactly what shapes, moons, or surface features are waiting at Euripides, Polymele, Lucas, Orus, or the Patroclus-Menoetius pair, because every single flyby so far has defied at least part of what models predicted beforehand. That honest uncertainty is not a weakness in the mission. It is the entire reason a mission like this gets funded and flown in the first place. So here's where we land, more than 5 years into a 12-year journey that will not fully finish until 2033. A spacecraft named after a 3.2 million-year-old fossil has already surprised scientists twice. First, by revealing a hidden double moon locked in orbit next to a rock the length of 7 football fields, and then by uncovering a tumbling, battered, two-lobed asteroid frozen mid-story from a collision 150 million years in its past. What began as a story about one strange hidden moon has turned into something much bigger. A small, quiet spacecraft slowly rewriting what an entire generation of scientists thought they understood about the leftover building blocks of our solar system. Nobody expected the warm-up flybys to matter this much. And now that they clearly do, the 5 untouched Trojan asteroids still waiting ahead of Lucy suddenly feel less like distant footnotes and more like the true center of an unfinished story. We spent this entire video learning about rocks that have been sitting silently in the dark for 4.5 billion years, waiting for anyone to notice them at all. A handful of scientists finally did notice, and they built a spacecraft, launched it into the sky, and sent it chasing after that silence for over a decade of patient, careful work. What began as an overlooked assignment, a set of unimportant leftover rocks nobody wanted to study, has become one of the most quietly important journeys currently happening anywhere in our solar system. Somewhere out past Mars right now, moving through the cold and the dark at thousands of miles an hour, a spacecraft the size of a school bus is closing the distance on 5 ancient rocks that have never once been seen up close by human eyes. It carries a name borrowed from a 3.2 million-year-old ancestor, and in a strange way, it is doing exactly what that fossil once did here on Earth, quietly rewriting a story we thought we already understood. We started this video with one hidden moon that nobody expected to find. We end it with an entire spacecraft, still traveling, still watching, still years away from its biggest answers, carrying every one of us along for a journey most of us will only ever witness through a screen. Somewhere out there tonight, Lucy is still moving, still listening in absolute silence, still closing in on rocks that have been waiting 4.5 billion years for exactly this moment. Keep that thought with you the next time you step outside after dark and look up. Somewhere in that same sky, invisible to the naked eye, a small human-built machine is quietly chasing the oldest leftovers of everything that ever became us. Few people even know this mission exists, quietly gliding through the dark for over a decade while the rest of the world moves on to other headlines. But the truth is, all of us are connected to what Lucy eventually finds, because those frozen ancient rocks hold pieces of the same raw material that once came together to build our planet, our oceans, and eventually, every single one of us. We do not need to be scientists to feel the pull of that story. We only need to look up and remember that somewhere out there, the past is still quietly waiting to be found.